Yeah, here, let me start recording. Yeah, I'm okay. Like, I'm not. This is not like a lecture or anything.
Yeah.
So I'm gonna do my best here to do it right. But yeah, like grid world is usually like the easy example that's given with a lot of this stuff, where say you're in a grid, right, and your agent is here, and the agent can take, say, a couple of different actions, right? You can go left and right, up and down. And say this is sort of your, you know, the value, the 10, and this is your terminal state. So this is like your goal, right? And say here is all zeros. So in other words, your agent wants to arrive at the goal, essentially. You know, so I don't know. This is turning into more of like a what is reinforcement learning thing, though, because this is just a good way to kind of visualize what a policy is trying to do, right? Because if you have this discount factor of zero, this agent is going to essentially like have a really tough time with this sparse signal, right? Whereas if your discount factor is greater than zero, it's going to, but not one, then it's going to try to discover what's the minimum path. But if the discount factor is one, then it doesn't matter how long the agent ambles around until it finds this value, because if it takes 20 time steps, or if it takes 5, it's the same value. So in this case, you're penalizing longer time steps, whereas here you've got you're only providing immediate value, but here you're not penalizing time at all. So okay, so like back to the policy here, the policy can be done in two ways, right? You can do this idea here with grid world is like value iteration. But this is actually, by the way, why grid world isn't often used for policy gradient, because the policy gradient kind of says that we have a stochastic, like often what you have in value iteration, right? What you do is you go max the argmax of an action for your like QS or something like that, right? And what this is saying is, and this is in a deterministic policy, when you have a policy that says I'm going to go up or down or left and right, right? This is saying, okay, well, what's the value of taking this next this next action, right? And I want to figure out, well, if I take action, if I go up, the value of that is 0. If I go down, the value of that is 5. If I go left, the value of that is 3. And if I go right, the value of that is 1. So I'm going to choose 5. I'm going to choose this one. It's the biggest one. I get the biggest value, right? And this is sort of this argmax thing. But that's like not really representative of like the real world, and then also of like, most of the problems that we deal with. Often we're dealing with a policy that is more like a distribution. And so I have a policy, and the likelihood of choosing an action is just like it's a probability distribution. So often this is parameterized by some kind of theta. So for example, theta could be a uniform distribution, it could be a Gaussian, it could be a neural network, and often that's actually exactly what it is, right? It's like a neural network parameterized by thetas that then is used to give you like the standard deviation and the mu or something of a multivariate, or like a soft max or something like that. But that's a little bit beyond this. For reinforcement learning, I think we're getting kind of off track a little bit, I guess.
How
So
expensive would, I'm so sorry. How expensive would something like that be to implement?
okay, so it can be expensive in, okay, the context of so once you have a policy, we haven't really talked too much about like how the policy functions. And again, like I'm not trying to like do a bottoms up reinforcement learning lecture because a lot of these things are all over the place. But say you have a policy, like, okay, let me clear this out because it's getting a little messy. So you have some neural network, and this represents your policy, right? And this is supposed to, you put in some stuff, and then you get out the action, or you get a distribution of the action, right? The probability of a given action that you can then sample, essentially. And the way you do this is say you have a 0, a 1, and so on, you would get a bunch of these logits, which is usually the way it's done. So like you can do this with a softmax, right? So say you have like the real way this is working is like you have a 1, a 2, a 3, and so on. These are just like imagine like a fully connected like neural network layer, right? And these are each one, like this is the number of actions that you have. And then you put this into a softmax distribution. And that will give you the, well, just to be pedantic, arg max of the softmax of the logits. So if you, I don't know if you're familiar with the softmax, but it's basically like, you know, you're taking the value and you're dividing it by the sum of all the other values, and whichever one is the maximum, that's the one you choose. So it kind of gives you like a 10%, right, and 90%. And so you would choose this one. So in that sense, the cost of actually executing a policy given a particular like state is not that expensive, but it depends on the state. Like, how do you encode the state? So for example, in something like double Q learning, the DQN, so double Q, what does the N stand for? Network? No, it's
like the N.
Deep. No, it's deep. It's deep Q.
Oh, double dip Q.
Wait,
That's
right.
right.
I always forget
What
what
does
the
Q stand for? I'm sorry for the interruption, by the way.
No, this is what this is for.
What does Q stand for?
And also, Kimi, you mentioned like expensive in in what context? Or do you mean like with like computing resource, time resource, or like what specifically?
I was more concerned about just like computing resource. I guess like since I don't really know much about machine learning, when we saw a graph, I was like, oh, an ordered graph in order to see like, you know, where you could go and that stuff. And obviously that in my head, I was like, that's really expensive. So how does this work? But now that I kind of know a bit of like the way it was explained, it's like, okay, I see it now. Like that's not as bad as I thought it was going to be.
Yeah. Sorry, go ahead.
No, sorry, Aidan, you go ahead.
Yeah, so like if you're familiar with like A star or Dijkstra's, right? That actually is so the dynamic programming, like value iteration, policy iteration, is a form of dynamic programming. It's very similar, right? You're basically, you know, you're here, and then you kind of explore the graph, each thing, and so on. And then you, if you get to your goal, then I'm done, right? Even if this goes forever longer, right? So like A star kind of uses the exact same thing in the sense that it's kind of checking these like these well, A star being a bit more heuristic than you know, Dijkstra's, but still same idea. So and when you talk about value iteration and like grid world, for example, grid world will use exactly the same thing, right? I'm here. I'm going to check all of the nodes around me. I'm going to choose the one that's the best. I'm going to check all of those nodes. I'm going to choose that one that's the best. But if there's one that I've already seen that's better, I'm going to go that way, right? It's literally just Dijkstra's algorithm at that point. So here, actually, this policy gradient thing is a little bit of a divergence from that, because instead, what I'm saying is I'm going to give you the state that I'm in, and I don't care what's out here. I'm still going to figure out what the optimal action to take is. So it's almost like I'm looking at the position in the graph that I'm in, and that's all the information that I need to make the optimal decision. And this is obviously a trained network, meaning that these parameters are not known when you first, implement this algorithm. So this is a neural network, right? And you somehow train this, and actually that's exactly the subject of this paper. How do you train a policy? Like, well, how do you train just the policy based on your state? So the complexity of this is a lot to do with the structure and the architecture of the network. It has to do, which has a lot to do with the representation of your state. So for example, in double Q, like the Atari DDQN, what they did is they represented state with 3 different frames of, and this was also, so this was like frame 1, 2, and 3. And these, I think, were like, I forgot what size the images were. I think
like
it was
84, 84 by 84.
Yeah, so it's like 84 by 84. I think the neural network was implemented as a convnet.
Mhm.
So that's less computationally intensive than a fully connected network. But by no means is this a lightweight network, right? Like you've got multiple layers of a convolutional network. So in total, you're probably looking at 50, 60,000, if not 100,000 parameters. I don't know what the exact numbers are. Like some of the networks that I'm training are like six gigabytes in total size, right? So that's kind of like, okay, well, where's the cost? How do you calculate what the cost is when you're dealing with these massive networks?
Can I add something, Ida?
Yeah, of course.
Yeah, so like also like from my experience as well, like you'd also find like representations like that sequential datas, like for example, a text. Like I've been reading like a paper where they have a text like an instruction, and so with that you have to use like an LSTM. So you have this network taking an LSTM that is reading sequential data and also taking frames with like a convnets or resonance, and also vector observations, which is regular multi-layer perceptions, and like and you have these giant parameters, like you said. But like another thing that can also increase the computational cost is also with impulsive gradients, you have the chance to actually sample um, in your environment through multiple simultaneously through multiple workers or actors. So that's something that's also dependent on how many CPUs you have as well and cores. And but like I was going to select to also answer your question together what Aidan said. I think the major part, because it might sound scary about all these hardware requirements, but the major part is actually the problem that you're trying to solve. If it's a trivial problem, you may not, and of course the state representation, if it's something that can easily be solved with just vector numerical observations, then you may just be good with just using a regular feed-forward neural network and simple structure, and which may be better because you may not overfit too, which is a problem as well. So yes, it's still exciting though.
Thank you so much.
Yeah.
Yeah, it's really cool. So this policy gradient, I don't believe deals with continuous actions yet. So this is an older paper. But since this paper, they've shown ways to deal with, so actions here are discrete, meaning I go left or I go right, right? There's no like amount. It's like I go left or right. There's no choice, but often decisions have to be of a magnitude. How do you make a decision of how much to go left or right? Or say you're like flying a plane, and what do you set the throttle to? Those kinds of decisions are continuous decision spaces. At this time, this was discretized down into discrete decisions. But yeah, we can talk about like that's I think I forget. I think soft actor critic was the first time it really was introduced.
Yeah, the solution like they have, I know like it's, which I've used as well, is like you said, this if it's a continuous action, you can find like a minimum or maximum of like like the range of the continuous. I know like in project I was working like with robots, and they're like sending like talk values to like a joint of a robot as a continuous value. So I sort of had to like discretize it into like bins, like into like maybe 5 or 6 bins, so it's still breaking it down so you can still work. But like you said, like other algorithms, there's some other algorithms that are better suited for continuous algorithms than policy grant. Also, I didn't know how you wanted us to like go through like the papers, because I mean personally I had some. I'm not the greatest mathematician. I'm better at implementing than reading the math. So that's why I was really more excited about this, because some of the maths just go to my head. I'm like,
Yeah.
I feel that. Sometimes like I'm reading papers and then like just gets like this huge wall of equations and it's just white noise. I just keep reading.
Like give me a Python script and I would get it working. But outside, but like with Aidan, it's like talking to him like in next lesson, like it's also really important to have the two ways.
Yeah, I mean, I'll share with you, right? Like my approach to this stuff is I want to really understand how it works fundamentally. You know, because I'm new to this too. You know, I've started like my ML journey just a few years ago. But I also want to be able to build the system. So that's why I've actually approached this in a mathematical way, but also in a like, hey, let's build some stuff way too, right? So I think the two are good. This paper, that's actually why I suggested this paper, because the policy gradient, and we can go through a different proof, because the proof in here has kind of, this was like the first time they proved it. And it was like a new result. But since then, the nomenclature has changed a fair bit. In fact, I can just, this is not, let me, this blog is actually like a really good, like Lillian Wang in general, like all her blog posts are terrific. This particular blog really breaks down. Like we can talk about the paper a little bit more, and then we can walk through her proof of it, which I think is, by the way, it's just a copy of the Bardo-Sutton proof that they actually wrote up in their book since this paper. So after like this paper, they wrote a book, and that book is like the staple reinforcement learning book. It's just called reinforcement learning. But yeah, I was just trying to give the background of this stuff, because what ultimately now you're trying to do is, instead of learning a policy based on the value and the iteration of the policy, like dynamic programming or what have you, you're trying to train the policy directly, right? You're trying to say, hey, I made this decision and that decision was wrong in some way, and now I can correct for that decision. I won't go too deep into like, I'm assuming you guys all are comfortable with like gradient descent and sort of how neural networks are trained. Yeah, so in essentially the whole thing of this is trying to prove that, so say you have this cost function, and all neural networks, right, have an objective or loss function, that the cost function is the derivative of the cost function is proportional to essentially the expected derivative of the policy. So that's sort of what this is actually like. The result of the paper is exactly this, right? Where it's basically saying, if I can somehow get the derivative of my policy, I can apply that derivative to the policy directly to improve it. And this sounds like really crazy, like how do you get a derivative of a policy? But if you've got a neural network, right, then the derivative of a neural network is very simple. You know, you just stick it into PyTorch and it tells you what to do, right? So that's the beauty of it.
Backward.
What's that?
A step backward.
Yeah, optimizer dot or loss dot backward.
Yeah.
One line.
It was so funny. Like that was always like my biggest obstacle. I'm like, how do I do this? Am I gonna write like all the differentiation of all functions? And then I realized PyTorch was like, yep, just step and backward and you're fine. And all the taters that I see in papers just like feel like it's just like a black box after that.
Yeah, no, it's agreed. I've had to implement LSTM backprop too many times with NumPy to be proud of it, you know.
Yeah, that is sick.
Yeah, so let's dive into the paper a little bit, and then I mean, but that's kind of the gist of it, really. I mean, we don't have to read it, right? But this sort of what it's saying. It's basically saying that, right, for any MDP, and MDP is a Markov decision process, we were talking about this earlier, that in this case they're using P or rho as the loss function, right? That this is the derivative of your loss function is equivalent to over all states, over all actions, the derivative of the or the gradient. It should be the gradient, but this back then they didn't have like neural networks. This was like with linear models and stuff. So you were literally where like the policy was equal to something like this, where it was equal to like this plus times x1 plus, you know, like just like a traditional linear model. So in this sense, they were just doing, you know, that, but these days, right, it's usually seen as a gradient because it's like a multi-dimensional network. But that's the entire result of this paper. And it's really powerful because now I can, as long as I can sample states, right, and I can run my algorithm, I can simply plug them into this equation and then improve my loss every single time, which is pretty cool.
One thing that was actually also cool was like, because I know most people think of it as like the loss, especially when you're working with supervised learning problems. But like I remember like in policy, something I read, I think that really hit today was like in policy gradient, it's not more about the loss now, it's more about trying to, instead of climbing down, where we're trying to maximize the return now. So it's almost like the trying to optimize the policy to like maximize like the return versus the idea of trying to minimize the loss between um, between a true and the actual result from the policy.
Yeah,
So
yeah, thanks for catching that. Yeah, when in reinforcement learning, you're not reducing the loss because you don't know what you're maximizing the reward. So to your point, it's a gradient ascent.
accent, yes, that's the word.
Although in practice, you just put a negative sign in front of things. It's not the exact same thing. So, but yeah, but it's cool. The paper goes into a little bit of baselines as well. So this sort of kind of digs into, you know, just showing that if you have okay, you have this Q function. The problem with the Q function, just like the value function, is this like it's like this imaginary value, right? Like how do you know what your Q, like how do you know what your state and action pair are worth? You don't. So often you would use another function to predict that in some way. And this sort of just this part of the paper simply shows that if you have some approximation of your Q function, you can use that as a baseline to predict. And this sort of like fits into actor critic, because at this point actor critic was around, but this just shows that you can use actor critic in the context of policy grading. So that's all this does, right? It just shows that if you subtract from your Q function a function that approximates your Q function, yada yada yada, you get to this, which is the same thing.
that's also as easy as just after having like your action, like your outputs from your neural network, just branching out another node to predict another value that is continuous. And that is, I believe that's this value, right? For your I was gonna I was gonna ask you a question. Like I know like it kind of feels like not everyone here is very conversant with like reinforcement learning problems and some of like the like terminologies and the problem in general. And like I didn't know like how you think because I know you mentioned that because this is the first time we're meeting, it's the first time I'm doing this. I know you've been doing this for a while with Unity and the rest with more professional people. So like I know like how do you think would how do you think we can work on that just so people who may be interested as well, like this guys can.
Well, you know, this is our first one, so I expected it's going to be kind of up and down, and we'll have different sort of folks with different backgrounds and that. So figured we just kind of, you know, barrel through it and see what happens. But what yeah, like after we kind of have gone through the paper already, I'm happy to go through the mathematical proof if that's of interest to anyone. But if not, you know, we can also talk about what paper we do next and what we approach there and at what level, right? Because we can always go and have kind of a, you know, we can find a paper on sort of more like value iteration. Let's start with value iteration or MDPs or, you know, bandits or something like that. But let's take the temperature of the room after. But yeah, I mean, do you guys want to go through the proof? No worries if not.
Yeah. I would appreciate it just to maybe get over my fear of proofs in math.
That's one yes. All right, I guess.
Yeah. But I then also to more like your suggestion, I wouldn't be I would love the idea of actually even going to more big reinforcement learning based algorithms versus even deep reinforcement learning, because I feel like that'll be an awesome foundation for everyone, myself too, because that's something I've always wanted to do, to go back to the roots.
Yeah,
Because it's harder when you're seeing all the staters everywhere if you don't really understand the basic notations and the basic reinforcement learning itself from Sonnet. So
yeah. How about next time we can do? Actually, there's a really great blog post. This one actually, or this one is really great. It's long. It's a very. I mean, I was just like, you know, I always use this to kind of spruce up on my knowledge because the problem with a lot of these algorithms, like as I'm sure you know, it's like they're all very similar with like one little thing is different. Like all the equations kind of look the same, but then when you look closely, it's like, oh wait, that one thing is not the same. It's like that t is a t+1, or like, oh, that's not a v, that's a q this time. Or it's very like subtle differences, because I think up until deep learning, reinforcement learning was very much this field of like very math and very programming, like computer science heavy, like how do we solve these dynamic problems, but they didn't have the tool like the deep learning and the machine learning tools yet. It was a very different, it was almost kind of very fundamentally different machine learning field. But with deep learning, the whole thing kind of like, because when you look at reinforcement learning, there's a lot of unsupervised stuff that's going on, but we didn't have unsupervised learning, I think, up until deep learning. Like we did, but it was all like statistical inference type of approaches or Bayesian nets. And honestly, Bayesian nets and Markov trees, Markov processes are kind of the same thing. So, you know, anyways, we could, how about we do this one next, or we can choose a section, because this is quite a large thing. Like we could maybe choose kind of, oops, up until here, you know, up until Monte Carlo methods.
I think this blog post would be a good starting point as well, considering I am at the lower end in terms of experience. Like I have just barely learned how to do basic neural nets in TensorFlow and stuff like that. So I'm just kind of starting out.
Cool.
And getting into the whole field. I feel like this last paper was kind of over my head by a long shot.
That's okay. Like this is not a class, right? This is a
right.
Yeah, this should be fun. Yeah, I love that. I'm constantly reading these things over and over again, and I'm by no means like an expert. So I would love to do the back to basics stuff. So let's do that next time.
I think what
Sounds
may also
good.
be great would be like because like me also, I'm trying to learn as much as well, especially like with the math, and which is where I feel like I would really learn more. But one thing I feel like can also be helpful with together is also maybe we can also have like a 10-15 minute session where we also have like a practical in a way, like just implementing like the basic multi-color in Python, and using like a simple uh, frozen lake environment from Gym to show like how it trains. I feel like that would like take it home for most people and for everyone. So
I mean,
to practice and just spare time. So I guess.
yeah, I mean, I'm down to do that. Like, how about this? How about we do this this part of the blog post next time,
Mhm.
and then the time after that, we can do like you can put together a little workshop. Because I don't think it's going to take 15 minutes, like to be
Yeah, it will.
take more. But that'd be fun. That'd be fun to do like a workshop together. Yeah, like a frozen lake thing. that'd be fun. Let's do it. By the way, like I don't know how everybody found this, but we can use the Discord channel, that MLAI Discord channel in my server, or we can do it elsewhere. So just let me know. But if you don't have access to that Discord, let me just post it in the chat right now.
Yeah, I found this from an ad that was posted in the AI Club server.
Yeah, sorry
just
about not
earlier today.
responding.
Oh, that's okay.
Yeah, I just saw it around. I was like, oh, sure, I should respond to everyone.
I was on a hike with a friend and like I checked my phone and like I got a notification from your server and I was like, well, I haven't heard from like this in a while. And it's like, oh, that sounds interesting. I'm interested.
Yeah, I think, you know, I don't know much about, so I'm an adjunct professor at RIT. So, and I didn't go to RIT, I went to a different school. I don't know much about RIT's like programs at all. Like I teach for the IGM department. But I've been kind of on a march to do ML and AI, doing that at Unity, and that's what I'm going to be doing with my next company. But you know, so I've been very excited to like, I don't know how much RIT is already doing with AI and ML, but from my perspective, like this is, I mean, especially for you guys, like you're in school, right? I'm old by comparison, so you know, this is true for me, but it's even more true for you guys in that like ML and AI is going to be like a foundational thing that happens throughout your career in computer science and in the technical fields. Like if you're not, you know, if it's not on your mind, it should be, right? It's gonna eat graphics. That's already happening. I can talk about that sometime. It's gonna eat you know, obviously AI and like reinforced like robotics. It's already eating robotics, right?
Yeah, I'm actually it's sort of slowly eking its way. It's slowly like worming its way everywhere. Like I'm an electrical engineering major, but I'm doing research in AI with in that department, and it's gotten to the point where in our digital systems 2 class we're studying neural networks now.
Nice.
Yeah, I was so happy when my professor, he swore, because he's one of my best friends, he switched his entire syllabus. I was so proud. Like, thank you, sir, for trying to get the next generations.
Yeah.
Yeah. So my background, actually, I did electrical computer engineering as well. So yeah, like there's so reinforcement learning. Recently, there's a cool paper about utilizing reinforcement learning for layout, which is nuts. Like, I don't know if you guys have ever had to do like a proper VLSI layout of like a non-trivial design.
Yeah, what do you mean by layout?
Like cadence, like putting the transistor, like laying out the transistors, laying out the components.
Oh, like on a PCB or something like that.
I took a class for that. That was the worst class I ever took at RIT. It was painful.
Yeah, I did.
It's a painful process.
I did like a 5,000 transistor design, and I remember the layout part took literally 2 weeks of just sitting there in front of cadence, just like a zombie, just like square, triangle, square, like I guess whatever.
Yeah, it's a lot, and that's I have like a little bit of PCB experience from EVT, like electric vehicle team. But we do all that manually. We don't have like any kind of anything do that for us because our boards are small enough. But for something with that many parts,
yeah,
I can imagine it would take a while.
Yeah, my first company, we did hardware, and I flew out to China, and we worked with like 30, 40 people teams. That's all they did was just board layout, right? Like all those jobs, AI will do those things. I promise you. It's and it's a hard job, but it's getting eaten. So like this is the future, and it's, I think, important. But anyways, okay, so we've got this for next time. Feel free to use the channel, the ML dash channel. It's in the chat.
In the chat.
I posted an article. It's just like, because you said about you know, machine learning and graphics, which is where I tend to stay. And this is an article that I found when I was working on my research, and it was something that I found really interesting, but it was just completely out of scope. And someone will understand it, and it won't be me. But
well, if you guys have time, I don't have too much time. I can't stay too late, but I can show you some of the stuff that I'm doing at Unity, one of which is this network called generative query networks, which actually render a scene from an arbitrary view, and it's entirely machine learning powered. It's kind of nuts. Ooh, Tel Aviv University. I'm Israeli, so I get excited.
Wait, that's awesome. My family's from Tel Aviv. Part of my family's from Tel Aviv.
Nice. Yeah, I was born there, but I grew up here. I'm trying to look like, what are they doing?
Kimmy, if you're looking for like computer graphics stuff, there's this YouTube channel called 2 Minute Papers. I don't know if you know about it.
I do.
But yeah, okay. I just wanted to make sure you were aware of it because I watch his videos all the time, and he does like exclusively graphic stuff.
That's awesome. Yeah.
I don't actually have to live in right 8:30.
Oh yeah. Okay. So let's we can kind of quickly go through this. And then yeah, like feel free to post papers in the channel. I'll post the stuff that we'll do next week, and then we'll figure out the week after, and then we'll do the workshop and all that.
Oh, one thing I didn't, so I know this time actually clashes with the RIT AI meeting time, general meeting time, and I mean this sort of seem interesting. People will reach out to me, and it's wild because we don't really have the highest of the closest that we have like talk meeting about deep, how do I put it? The closest to this field is deep learning. That's what I'm trying to say. Like there's really nothing like this focused on reinforcement, deep reinforcement learning. Even the courses in the CS department just have few lectures or 1-2 lectures in reinforcement learning, and that's it. It's really, so this is the closest anyone in RIT currently can experience practical knowledge and reinforcement learning, believe it or not. So like
No pressure at all.
yeah, so like it would be awesome if we can so fix, since there's someone here who's in the RIT AI club, based on their time, if it's sometime like in a different day or something.
Okay.
Maybe
Yeah.
Thursday.
Let's talk about it offline. I'm happy to change the time that I'm in PST. I'm just in California time, but my 5 o'clock to 8 o'clock is I have 2 kids, so that's like kid time. That's like, you know, fight them into a bath and then fight them into bed and then keep them. So but let's talk about it. I'm happy to change the time to accommodate people's interest in this. I love, that's surprising that there's not much reinforcement learning stuff going on, but yeah, this is an interest of mine. So, you know, especially in imitation learning, like can't wait till we can talk about this. Man.
Yeah, I would love to learn this one from you, to be honest. And I read the paper and it wasn't as easy as I thought it was.
It's basically, well, okay, like this one honestly isn't that complicated. It looks more complicated than it is. Like it comes down to, where's the algorithm? Here. Like everything kind of distills down into this. And the idea is that, funny, see, you can see this is the policy gradient right here. What you're doing is the reward signal is just the discriminator output of a GAN. That's it. The whole paper is right there in that one line.
It looks like a headache, but it's not.
Yeah, it's basically saying that, you know, we're trying to discriminate whether or not a action is okay. Here's okay, we could talk about this paper a different day, but this whole idea is it's trying to imitate an expert trajectory. So you give it a bunch of trajectories from experts, meaning human beings that are playing a game or something. And then it trains a discriminator that can discriminate between an expert trajectory and a fake trajectory, meaning a trajectory that was output by some other network, right? And this trains it such that this other network can generate trajectories that look like the expert trajectories. This is like a GAN, right? Have you ever seen like these GAN networks that can produce spaces of people that look very real? The same kind of mechanisms that play, right? You have a network that's outputting garbage and another network that's saying, that doesn't look like a face. And then that network's like changes something and like, that doesn't look like a face either. And so like they keep doing this for a long time, and eventually this network's outputting images that look like faces. So in this case, instead of faces, it's actions, right? So like this network's outputs a trajectory, and then the discriminator like, that doesn't seem like something people would do, right? And it's like, okay, let me change a few things. You rinse, repeat, and eventually now you have a generator that can generate expert trajectories. that look like a human being's playing the game. And the whole, and from a reinforcement learning standpoint, it just distills down into this, just the output of the discriminator is your reward signal, which is kind of fun.
Okay,
This is a deeper dive paper. Like, it's worth going into the theory here. I'd need to reread the paper because it does get a bit hairy.
Well, but one thing I love about all the papers, even though I haven't gone, I see like H and I know it's entropy because it's like very universal among all the papers. So like, I think that's why it would be an awesome idea if we start from the ground up, because when we start reading complicated papers, we see like all the symbols are like pretty much generalized. So it won't be, it's confusing now, but I bet when we read multiple papers before here, it's like, okay, now I know what that is.
Yeah. The concept of like maximum entropy pops up a lot in reinforcement learning, because in reinforcement learning, you really want to generalize your thing that you're doing. And so you not only do you want to learn a policy that works for the data that you've seen, but you also want it to generalize to data that you haven't seen, because the agent's not going to see all the data in the world, right? Like, it's kind of like the example, like, I can only live one life. I can't live, you know, a million lives and then choose the best one and make my decisions based on that. And so you want to have some kind of way to make decisions under uncertainty that maximize the like entropy that isn't specific to a particular niche kind of set. Because like, okay, like that guy's a rock star. Okay, if I choose to be a rock star, there's a very high likelihood I won't get the same path as that person, right? And that's the idea, is like, okay, well, we've got these outliers and things like that, but we want to smooth that over. And one of the ways to do that is using maximum entropy. But we can talk about that too.
Right, and actually have to go now, but
yeah,
definitely.
We're out of time, so we'll do the let me stop the recording, but we'll do the policy gradient proof next time. How does that sound? And then we can dive into we'll do that blog post as well, this one, through Monte Carlo methods. Sound good?
Yeah,
Perfect.
And then Dewey, we'll talk about how to change the time that works better for the AI folks that are interested.
Yes, that's right. I can also post on the machine learning club as well.
Awesome. And I've recorded this, so I'll post it to the channel. And yeah, thanks to everyone for showing up. You know,
a big crowd for the first meeting, right?
yeah. I mean, this is honestly like, our reading groups at Unity have fewer people, so.
Yeah. All right. Nice to see everyone.
Yeah. Have a good one.
Yeah, I'll see you guys next time. Thanks for doing this.
This is cool. Thank you.
Sorry, we didn't have introductions.
Bye, everyone.